Good morning, friends. So it's my honor and privilege to be here in this workshop, talking to you and interacting with you. When I was first told that I'm going to be one of the resource person for this training workshop, I was a bit hesitant because uh, I don't teach so much. You people teach a lot, so you definitely know better than me what teaching is. Um, our focus is largely on research. So today I will basically share with you something about light, optics, and telescope. That is the topic that is given to me to discuss. I have also tried to make it as interactive as possible because that's like making it less boring. You're going to sit through for 7 days and hopefully I have not made my presentation very dense with mathematics and other things. I kept it as simple as possible. So, okay. Let me ask you, what is learning? Before I go to telescopes and optics, because teaching involves learning, right? And both at teaching level as well as students level. So let me ask you, what do you think learning is? Just quickly, you can raise your hand and just tell me what you think learning is. What do we mean by learning? Yes. Okay. Right. Yeah. That's one way of looking at learning. Yes. Continuously acquiring knowledge. Yes. Getting new ideas. Yeah. Anybody else? Understanding things. So learning is a multifaceted process which of course involve, it's getting stuck. What's, yeah, why? This is how it is going to work. Okay. So learning is a multifaceted process which involve acquisition of knowledge, skills, behavior, attitudes, or value through experience and instructions, right? So whatever you told is also correct. That's what we mean by learning. And at most fundamental level, learning is about forming connections, connection between ideas, between our experience and new knowledge. And whether it is a child who is marveling the beauty of rainbow, or an astronomer who is trying to uncover the mysteries of the distant galaxy, learning empowers us to see the world in different ways or new ways. That's what learning means. But then the question is, how does this process work? And what are the obstacles that come in the way of learning? And how we can effectively learn? So those are the questions that you all must be grappling with, right? We all do that. So then the question is, what are the major obstacles in learning? So again, I put this to you because you are teachers and you know a lot about students, what difficulties they face. So what do you think are the major obstacles or difficulties in learning? Not finding proper resources, yes. Why do students find things difficult to learn? What could be the main reasons? Language barrier is also one of the reasons, yes. Not keeping things simple, right? There's a lot of jargon. We can make things very difficult in terms of language and so on. Yes. Lack of interest in subjects. Yes. Anything else? Okay, so I have listed some of these which you have already covered. The first is lack of well-defined learning goals. If we are not sure what we are going to learn, then learning suffers. Okay, And sometimes there is unnecessary jargon and complicated language, as sir has pointed out, that also makes learning difficult. And sometimes learning is also blocked by these preconceived ideas and notions. So we already have something in mind and we are reading something else. So it doesn't help us to learn. Like somebody who is going to learn about evolution, if he's already kind of biased by intelligent design, then he would find it difficult to learn, right? So those are the preconceived ideas and notions. And also inability to connect classroom learning with outside world. So that is the major obstacle that most children face. What they learn in class is a different universe than what when they go outside. They are not able to connect. Why are we learning linear algebra in the class? How is it applied to the day-to-day life, right? So that's another gap in the learning process. And sometimes we have flawed mental models of physical realities. Again, we think we already reconceive some kind of preconceived notions. For example, seasons. When I asked students what causes the change in seasons on the earth, many students end up saying that it is because of the earth's orbital distance changes, which is not correct. Season changes happen because of the tilt of the earth and not because earth goes closer or farther from the sun. That has very little effect. So these are the major obstacles in learning. And then the question is, how do we make learning more effective? So people who do research in pedagogy and other things, there is something called learning pyramid. And what it tells us is that there are majorly two ways of teaching or learning. One is the passive teaching method, which currently what I am trying to do, giving a lecture or reading or audio video or demonstrations. So those are the things, they are somewhere here, but they are not very effective way of learning. Okay, but what are the better ways of learning? Better ways of learning are like participatory method, where you engage students in learning, engage through activities or engage through like discussion group. Then what is that? I can't read it. The practice by doing, right? Doing the experiments and so on. And most effective way of learning is by teaching, right? So that's why teachers are also good learners. All right. So that is about what learning is. Now let's change the gear and come to the topic. And topic is on the light. So what is light? So light can mean different things to different people depending on the context. Okay. At some level, we say, or scientifically we say, light is a form of energy which can be both, which can behave both as wave or particle, right? But for many people, symbolically, light could mean or light represent knowledge, hope, discovery, or spiritual awakening, and so on, right? So light can have different meanings because it's such a broad term. So actually, the story of light is also the story of human history, if you look at it, right? Because on Earth, it's the light which provides the warmth. It also provides the vision for us and also drives lots of processes which are responsible for sustaining the life on Earth. Okay, and light has also been central to human curiosity and progress, right? Right from the days when humans learned to harness the power of fire. Okay, they knew what light is, and to the modern days when you have these very powerful lasers to produce light for various other applications. Okay, so light is also window to understand the universe. It holds the key to the numerous mysteries of the universe. And light, it's possible to manipulate light. You can bend light, you can reflect it, you can scatter it, and you can transform it the way you want. And that also leads to lots of applications that we use in light basically are based on these principles or these properties of the light, which we will be talking. Now, light has direct and indirect impact on every aspect of human life. It is central to science and technology, art and culture. Wherever you see, the light would be playing some role or other. If you start paying attention to the details, it will become very obvious. So light technology also powers innovation and progress in lots of industries. and it's also a major economic drivers for the nations. So the role which electronics played in 20th centuries, the light is going to play that in 21st century. Okay, so which means it's important for us to promote understanding and awareness about light at all level. And how does it happen? It starts with teaching. We teach about light in the right way, which eventually leads to a good research, and finally to innovation. And that's the process of technological innovation. Now, scientifically speaking, actually there is no single definition of light, which is a good thing. It's good not to have one definition of anything. And at most basic level, light is a form of energy, and typically when we teach it in college level, we basically have two models of light, the particle model of light and the wave model of light. So particle model of light treats light as photons, the tiny particles which interact in certain ways, and the wave model of light treats light as a wave, basically the disturbance, electromagnetic disturbance which propagates in space. Now the question is, how do astronomers study the universe, right? So you would be surprised that light, it's quite apt to call light as a cosmic messenger. That's because 99% of the universe that we know today, that knowledge essentially is derived from the light that arrives from the celestial objects, from galaxies, from stars, from nebula, or whatever we know about the universe. We know a great deal about the universe, and what I'm saying is that 99% of that knowledge is built from the light that we receive from these objects. Okay, so light means electromagnetic waves, and only the 1% of it our astronomical knowledge come from, for example, high energy cosmic rays, neutrinos, gravitational wave, or the rocks that space missions bring to Earth, or sometimes from meteorites. Okay, so that's enough to set the stage that why light is important for the astronomers or for us to understand about the universe. So essentially, light covers the entire electromagnetic spectrum, going all the way from visible infrared, radio, UV, X-ray, and gamma ray, and so on. Okay, and what do astronomers do? They essentially, at most basic level, they measure the position of the stars, their brightnesses, their distance, temperature, mass, velocity, compositions, age, and everything. So all this information is just inferred from the light that we receive from stars. So that is something very spectacular. Now, that light, how do we collect that light? And that light is collected through the telescopes. So what is telescope? Telescope is a very simple optical instrument which help us to collect light from celestial objects. Telescope also make things look bigger, right? And telescope also provides better resolution. We'll cover these things a little more in detail. But so there are different types of telescopes. As I said, light spans a broad wavelength range, all the way from radio to gamma ray and so on. So there are radio telescopes, something like this, radio dishes. There are optical telescopes. So these are some of the examples of 2-meter telescope that we have in play. This is a 2 Keck telescopes in Hawaii. This is typical telescope that amateur use for sky watching. This is a Hubble Space Telescope which is in the space, operating from 1996, and this is the example of JWST, which is making lots of news recently. This was launched in 2021, and it's making many new discoveries which were not possible earlier. So to understand how light works, we need to understand so what telescope? Telescope is basically at basic level it's a lens or a mirror, right? And it forms the images of the objects. So we need to then understand how a mirror or a lens forms the images. So it is based on simple laws of reflection and refractions that you all are aware of. I'm not going to repeat those, but all I would point out is that, let us say, if you have a lens, it's a convex lens, which is receiving parallel rays of light, which are coming from a source which is at infinity, right? And the lens would bend these rays of light to a common point that we call focus. And the property of the lens is that the rays which are closer to the periphery are bent more, whereas the ray which is going through the center is just goes straight. So it is doing uniformly to these set of rays, right? And this distance, the distance from the lens to this point where all the rays converge, is called focal length. Okay, so if you had a star somewhere at far away distance, the image of the star would be formed here. Okay, but let us say it's not just to image stars. Lens can also be used. All our smartphones have very fancy lenses, right? But the principle is same. So you have some object that you want to image, you want to take the image of that object, and that object can be anywhere after the lens. And depending on the distance of the object from the lens, its image would be formed at different points to the right of the lens. Okay, so if your object is beyond 2f, the image would form somewhere after the f. Okay, but in most cases objects are really at very far away distances, so your image plane more or less remains close to the focal point here. Okay, so that is what lens does, but the same mechanism can be achieved by mirror, right? All you have to do is take a mirror and curve it, right? So what lens was doing here, the refracting element, same thing can be done by the reflecting element. So you have a parallel set of rays which are hitting this concave mirror, and it's focusing at one point which we call as focal length, focal point. And here it is showing how the image is formed by this concave mirror. If there is an object which is kept at a distance beyond c is basically 2f, and image formation, that's a very simple rule of thumb. If you want to really see for a given object where the image is formed, you have to basically take three rays. One ray which goes parallel to the principal axis. Any ray which is parallel to the principal axis, after it refracts, comes to the focus, right? That's one rule of thumb. Second is, a ray should go through the center here, and that ray would not change. This is all simple application of law of refraction. This ray will go straight, and the third ray you should pass through the focal length, and any ray which goes to the focal point would emerge as parallel. So the place where all these three rays would meet would be the place where this point is imaged. So this can be applied to any optical element in order to figure out what is the nature of image that a lens or mirror forms. So again, I know you know it all. I'm just for the sake of completion, I'm just repeating it. And this is the equation which tells us how the focal length is related to the object distance and image distance, right? So coming to the refracting telescope. So as I said, refraction is basically, when does refraction happen? When the light goes from one medium to another. So it bends away or towards the normal depending on which medium it enters. So in this case, if this was the air and this was, let us say, water or glass, which has refractive index greater than air, then the ray of light which is coming this way would bend towards the normal, right? If this was a medium whose refractive index was smaller, then the ray of light would have bent away from the normal. So that's all is the law of refraction. You can say it, I sin theta is equal to r sin reflecting angle, and so on. So that's about refracting telescope. And telescope that we normally use for skywatch will have objective, main lens which collects the light, and also an eyepiece. So objective basically gathers the light and bends it to the focus. This is the focus. And eyepiece is a smaller lens which is with smaller focal length, is placed in in a manner such that the light after the focus becomes parallel. Okay, and that's where you put your eyes, and again eye is a lens, right, and it focuses this light back to the retina, and that's how you see the star, or that's how you see any object that you are trying to view through the telescope. Now for sky watch we use lens based telescopes, right, but for research where required telescope size is large, we do not use lenses, right. Lenses have certain problems. One that you are aware of is the chromatic aberrations, that a lens would focus different color to different points, right. So this leads to some kind of coloring of the image, which we call as chromatic aberration. And when you are doing scientific studies, when you're studying the stars or any other objects, you don't want such a thing to happen. You want a crisp, sharp image. Okay, so there are ways to overcome that. You can use a lens which takes care of the chromatic aberrations, but then there are other problems also with the lens. Some of these are here. That one, of course, is the chromatic aberrations. When you are using a big lens, its weight and size would increase. Okay, and lens also, you need to make the lens. If you're making a big lens, the quality of the lens or the material inside the lens has to be uniform, right. If there are any impurities, it would distort the image that you are coming. So it becomes more and more difficult as the lens size increases to grow a lens or to make a lens which is uniform throughout the homogeneous and uniform medium. And so once you have a big lens, it's also very difficult to support, right, because you are holding it from the edges. It has a large weight, so you can really track the object very well. Okay, so all the large telescopes or research telescopes are made with mirrors currently. Okay, and mirror means they work on the principle of reflection, and reflection is nothing but that angle of incident is equal to angle of reflection. That's all, right. So if you have a plane mirror, it's going to behave this way, right, but if you have a curved mirror, it will still behave same way, but the properties slightly change. Okay, so you have parallel rays which come, strike the mirror, this concave mirror, and it's going to focus all of them at this point, just like the lens does on the other side. Okay, so that is the principle of reflecting telescopes. My colleague Arun Surya will demonstrate you also how a concave mirror or paraboloid mirror forms the image and how it works. Now the advantage is that there is no chromatic aberrations, size is small, easy to manage, it is also low cost, and it's the big advantage is that you can support this mirror easily. It doesn't have to be very complicated or system to support that weight. Mirror do not have chromatic aberrations, so they will work in the same way over a large wavelength range. Okay, so there's no wavelength dependent on the mirror, and that's why all the modern research telescopes are made of mirrors, or they are all reflecting types. Now here is the example of different configurations of the telescope depending on our requirement. So if you want to put an instrument, so this is called prime focus telescope. So you have a concave mirror, the light from the star come shown like parallel rays coming, and that's where it's going to focus. This is a prime focus, means the first focus, right? So you can put a small instrument here to collect that light and analyze, right? So that's one way of using a telescope. Another one is the Newtonian configuration. Now let us say if you want to see the star, there's no way you can put your eyes here because you would be blocking the light that comes from star. So the best or the one possible way is put a flat mirror somewhere here before the focus and deflect the beam outside the telescope tube, and here you can put the eyepiece and view the stars. So those who have seen or used the telescopes for night sky skywatch programs, they are largely Newtonian. Some of them are largely Newtonian telescopes. There's another configuration called Cassegrain, which is very popular, especially for the research purpose. So you have a telescope primary mirror, which again bends the light towards the first focus, and before the focus itself there is another mirror, convex mirror, which again reflect that light through a hole which is there in the center of the primary mirror, and that's where you can analyze this light. Okay, there's a CUDA version of it. CUDA version is something similar to it, but it's not just one flat mirror. There's a secondary mirror which reflects the light, and there is a flat mirror which again direct it outside the tube. That's where you can put your scientific instrument to analyze the light. And this is how typically the telescope would look like. This is the telescope tube. This is a guide main tube. So and this is the mount, right? And if I have to represent the ray diagram, that's how it would look like inside the tube. The rays coming from the star getting reflected from this mirror onto this hyperbolic secondary mirror, and then hyperbolic secondary mirror again focusing them somewhere here. So that's a point here where you put your eyepiece and see the stars. Okay, so then that was a simple introduction to telescopes. Now there are some questions, like important questions related to telescope, that we would like to answer in the remaining of the talk. And those questions are like, what makes a telescope powerful, right? Does the size of the telescope matter? If it matters, why does it matter? And another question is, do bigger telescopes see farther, clearer, or both? Why do we make big telescope first of all? Why do we need big telescopes? And where do we, once you have a telescope, let us say if you're keen to do research, where is the right location for installing the telescope on Earth? Can we do it in Bangalore? Can we install a big telescope in Mysore? Will it make sense or not? So that's another important question. And why don't we use lens instead of mirror in large telescope? That I have already answered. This thing, how do we avoid blurry images caused by Earth's atmosphere? I'm going to cover this later, what it means. If you have a large telescope, you are going to encounter some more challenges, and that is related to the turbulence caused by the Earth's atmosphere. Okay, so to answer those questions, we need to first understand what are the key characteristics of the telescope. Okay, so we can basically, there are 5 main features of the telescope which can help you answer all those questions. One is the collecting area of the telescope, how big your telescope is, right? It's a circular aperture. So the area of the telescope is basically given by pi r square. R is the radius, but here we are taking the diameter. Diameter is d, right? So d by 2 is the r. So this is the area of the telescope, which goes as d square. All right, and there's another important parameter which we call f number of the telescope. So f number of the telescope is defined as the focal length of the telescope divided by the diameter of the telescope, size or diameter of the telescope. So this is usually called f ratio or f number and denoted by f by d. Then there is another one called magnification. If you want to see how magnified your image is, then it's given by the ratio of the objective focal length to that of eyepiece. Okay, then fourth one is the plate scale. Plate scale, will come to it what exactly it means. Plate scale essentially tells you how much part of the sky is imaged onto the detector. We'll clarify that a little later. And the most important characteristics of the telescope, why we use big telescopes, is because it provides you a high resolution. Okay, what resolution means, that also we will see next. So first, collecting area. So as I said, collecting area of the telescope scales with its diameter. Okay, it goes as per, is proportional to d squares. So what does it mean? Okay, what does it mean to have a large telescope, and what what is its implication on the bright object or far away object. So if you are using a big telescope, what it implies is that either a given object will appear more brighter if you are using a bigger telescope, or a faint object can be viewed from a large distance, right? Okay, large telescope collects more light proportional to area square, right? So if object is placed at a certain distance, right, it's going to collect more photons, so it will appear more brighter, right? If the object is taken, let's say you have a faint object also emitting photon, is emitting less number of photons, but since you have a large area, it collects more photons, so the fainter object can appear brighter at larger distance. Okay, so that's the advantage of having large collection area or large diameter of the telescope. Now take an example of, let us say, 10 centimeter versus 50 centimeter dia telescope. So there are two telescopes, 50 centimeter dia and 10 centimeter dia. So their difference is, they differ by factor of 5. So area is going to differ by factor of, the diameter is differ by 5, so area will differ by 25. So what does that mean? That for a larger telescope, an object will appear 25 times brighter than 10 centimeter telescope, right? I repeat, if you are using a 50 centimeter telescope, an object viewed by 50 centimeter telescope will appear 25 times more brighter than the same object viewed with the 10 centimeter telescope. That's about the brightness. But you can also say that if a 10 centimeter telescope can see an object at a certain distance, right, that the faintest it can go to certain distance x, then 50 centimeter telescope should be able to see the same object at a distance which is 25 times more than x. Okay, so that's what it means. And another important parameter, as I said, is the telescope f number or f ratio, which is the ratio of focal length to diameter of the telescope. So you have lens here and it has a diameter d and it has a focal length f. Okay, and this lens is focusing all these parallel beams to this point. You have another lens f which focuses these parallel beam closer, right? So this is long focal length and this is short focal length. So astronomers call this as a fast beam because it's converged fast, right? It converges closer to the lens. It has a small focal length, so it's called fast beam, and this is called slow beam. So what is the implication of these fast and slow beams? When you have slow beam, focal length is large, so f in the numerator is large, which means your f ratio is large. Okay, so it's a large f number telescope and we are calling it as slow beam. So what happens if that is the case? So if telescope has large f number, it's going to have large magnification. Okay, large magnification also means small field of view. Okay, I'll clarify those things. And such a telescope, which is slow beam telescope or large f number telescope, it has a large magnification, so it's ideal to view image surface of the moon or the sun or the planet, because you want to see what are the details present on the surface of the moon, sun or planets, right? So you require higher magnification, so large f number telescopes is the ideal one for that. Why we use the small f number telescope or fast beam telescope? That is, small f number means your f is small, so f ratio is small. It gives you a wider field, right? Since magnification is small, it can many more objects can come in its field, right? So it's a large field and it's ideal to view star clusters, galaxies and the Milky Way. So these are all extended objects in the sky. They are spread over large area in the sky, right? And you want to see them at a time. So you should be able to see through the telescope all of them all together at once, right? Which means large field. Large field can only come from such a telescope which has smaller f number. So let's see what it means. Now this is an example of, the top image is example of large field of view. So this is an image of the solar disk of the sun. Okay, so entire field image is captured by a telescope. So that telescope will have large field of view and small magnification, right? But on the contrary, if you have a telescope which has large magnification, then that wouldn't be able to see the entire disk at a time. That can only see a part of the disk, but give you a magnified image of that, right? So this is an example of small field of view, but large magnification. So you can see the whole thing is magnified here, right? But the field is small. It's only covering this much. Okay. So let us take some examples. I have just probably answers are given. So let's say you have 50 centimeter telescope and 50 centimeter f10 or 50 centimeter f6, right? f10 means focal length is 10 times the diameter. That's what it means. Okay. So then the question is, which among these will provide you a brighter image? Which telescope will give you a brighter image? Remember, the small f number image has small magnification, right? The magnification is small, image is small, right? So if image is small, most of the light is going to be falling in a smaller area, right? Which means it's going to be brighter. So in this case, it is f6. Another example, 30 centimeter telescope, f8 or f5. So which of these will provide you more magnification? Magnification scales with f number, as I said. So f8 telescope will have a larger magnification compared to f5. The third example is, which one would provide you wider field? So you have a 15 centimeter telescope, 15 centimeter f6 or f8. Wider field, which has short focal ratio, right? Short focal ratio is f4. Okay, so I hope you got that idea. Now another important characteristics of the telescope is called plate scale or pixel scale. So just to demonstrate that, again I'm showing you light coming from a source which is at infinity and is getting focused at a focal point f of the lens. Okay, now this star happened to be on axis. Okay, so wherever it is, it's parallel. These rays are parallel to the principal axis. All right. And if there is another star which is slightly displaced, angularly displaced, then you would have light coming at certain angle. They are still parallel beam, but all of them are making some angle theta with the principal axis of this. So in that case, your image is going to be formed somewhere here. So this is star 1 and this is star 2, right? So there are two stars in the sky, and that's how they are imaged in the focal plane of the lens or the telescope. So let us say if you put your detector here, detector could be your photographic plate, or it could be CCD camera or camera that most of your mobiles have. Okay, so this is a linear distance or linear separation between the image for objects which has angular separation of theta. Right now this theta happen to be very small, so you can use the small angle approximations to just say what is tan theta. Tan theta is theta, which is in this case happen to be y divided by f. Okay, so plate scale we define as, so this is theta is equal to y divided by f. Y is the linear separation between the images of the star and f is the focal length. So plate scale is just, so you just take y to the denominator, so it becomes 1 by f is equal to theta over y, and theta is measured in radians and y is measured in millimeter, right? Earlier, conventionally, when astronomers were using the photographic plates, they are of certain size, and that those typical convenient unit to measure the size of the photographic plate was millimeter, and that's how it stuck. So radian per millimeter is the unit of plate scale. But again, another caveat, most astronomers don't work in radians. Even though it is a SI unit, we still prefer to use degrees arc minute or arc seconds, right? So we know that 2 pi radian is 360 degree, right? So we can convert this pi radian to 1 radian to how many arc second. So 180 into 60 into 60 divided by pi gives you a conversion factor in terms of arc seconds. So 1 radian is 206 to 65 arc seconds. So 1 over f, which we are defining as plate scale, becomes 206 to 65 per millimeter, arc second per millimeter. Instead of radian per millimeter, we are now calling it arc second per millimeter. So that was how people used photographic plate. These days nobody uses photographic plate, they are out of fashion. Now what we use is CCDs, these charge coupled devices, the quantum devices. And those are pixelated devices, and pixel size is usually measured in micron. The cell phone, smartphone that you have, those are CMOS cameras, and the pixel size is typically around 3 to 5 micron. Okay, very, very small. So this whole thing can be converted into the micron unit. Considering that S is the pixel size, which is in micron, I can write the plate scale as 206 into 265 into S in micron divided by per millimeter. So this becomes our standard unit for pixel scale. Just stay with me. Let us say, now taking example, it will clarify. I have a telescope of size 4 meter and a CCD camera or a CMOS camera which has 1K by 1K size, 1024 by 1024 pixels, and each pixel is 10 micron. Then question I'm asking is, what is the field of view, right? So to calculate field of view, first we calculate what is the plate scale. So plate scale, as I said, is you put these numbers here into these equations, and you get the plate scale to be 0.52 arc second per pixel. So 0.52 arc second in the sky is imaged onto 1 pixel of your detector. That's what it means. And since total detector size is 1024, you can see that the field of view is going to be 8.8 by 8.8 arc minute square. So that's the only field that this particular telescope with a 1K by 1K CCD camera can capture. Okay. Now this is 8 arc minute by 8 arc minute. But let us say somebody asks you, I want to image the full moon or full disk of the sun. What is the size of the detector that you should be using? Okay. So to image a full solar disk or moon at this plate scale, you would need, this is 8 by 8 arc minute by 8 arc minute or 9 arc minute by 9 arc minute. The size of the sun or the moon is around 30 arc minute, half degree. Okay, so which is like 3 times, roughly 3 times of that. So essentially this is giving you 1K. So 3 times of that means you would need a CCD which is 3K by 3K. Then only you would be able to image the full. Okay, now let's further clarify this. So in first case, all these images, the detector size is same detector is taking these images, but in first case the full disk image of the sun is taken, which is roughly half degree or 30 arc minute. In the second case is 1/3 of this image, just a part of this image which is taken here, and that is 10 arc second. And in the last case we are zooming into one of the sunspot, which is only 30 arc second in size, right? So this is your full disk image of the sun, this is a partial disk, and this is a high resolution image. Okay, and detector is same in all these cases, right? But so what does it mean? That the angular size that is imaged in each of these images per pixel is going to be different. Okay, so that's what we are saying what plate scale is. Plate scale tells us how much of the sky in arc second is measured per unit length on the detector, and in this case per unit length we are saying is per pixel. So large pixel scale means more sky covered per pixel, or small pixel scale means small sky covered per pixel. In that case, the question is then, in these images, Which of these images has largest pixel scale and smallest pixel scale? Pixel scale is how much sky is covered per pixel, right? To give you another clue, I'm saying that all these have same detector size. So let us say these are 4 by 4 pixels. So which of these images have largest pixel scale and which one has the smallest pixel scale? First one is what? Largest or smallest? Largest, right? Because the bigger sky is taking the full disk is being imaged onto this, whereas this one has smallest pixel scales. Okay, very good. So that's nice. Now the final element of the telescope, or final parameter or characteristics of the telescope, very important one, often we miss it, is the telescope resolution, right? Magnification is different from resolution. Resolution is the ability of the lens to distinguish two small features, right? To basically resolve small features or resolve fine features in the object, right? So how does lens do that? So let us say we have an point object which is somewhere in infinity, and we have a lens which is taking the image of that point object. Now this lens, the property of the lens is not to just give you an image of this. The lens would create an image of the point object with some kind of airy pattern around it, right? That's the fundamental property. That's what nature has endowed lens with, right? So this image is not going to be just like, the object is not going to be exactly imaged as it is in the image plane. It's going to be this we technically call as PSF, point spread function, right? A point gets spread in the image plane into this airy disk pattern, right? Now if you have two such points close together at infinity, the lens is going to image them something like this, right? So this is the image that you will get for these 2 point sources, right? And if you bring these two sources together, meaning their angular separation is reduced, then their PSF will also start overlapping, right? So you cannot really bring these two sources infinitely close together and still hope to resolve it. Now you must remember that one rule of thumb, or the property of the lens, the theta, the angular separation between two objects that telescope or lens can resolve, goes as 1.22 lambda over d. So it is inversely related to the diameter of the lens, okay? So if you take small lens, its PSF is going to be larger. If you take bigger lens, its PSF is going to be smaller. There is an inverse relation. So that's why the large telescope would create smaller PSF, which means they will be able to resolve finer details, right? So that's the advantage of using large telescopes. You can see many more details in the object. Let us say you are looking at the star cluster, you will be able to see individual stars. If you have small telescope, maybe you cannot resolve that. So let me just show you, again illustrated with this example. So telescope resolution. So we have let's say car with headlights on. The separation between the headlights is around 1 meter. So car is just few meters away from you. You can clearly, your eye can clearly see the two headlights distinctly. Okay. Now let's say move the car probably 200 meters or so. As it goes further, the angular separation decreases, but I can still see these headlights separately, right? Which means I is still able to resolve it. If you take the car, let us say beyond 3-4 kilometers, you will get the light, but you would not see the two headlights separately, which means at that distance, eye has lost the ability to resolve. Okay, so human eye is like a lens, but it is a very small lens of diameter 2 millimeter or 3 millimeter, and angular resolution is roughly in radian is 10 power minus 6 radian, which means in such a case it can resolve objects only up to 3 kilometer distance. Now if you had 1 meter telescope looking at a car whose headlights are 1 meter apart, it will be able to resolve it at a distance of 1500 meter or 1500 kilometer. A 10 meter class will do 10 times of that, 15,000 kilometer. So if you have a 10 meter class telescope and there's a car in California and you try to see it through 10 meter class telescope, you would still be able to see the distinct headlight of the car. 30 meter class telescope that can take it to 45,000 kilometers. So what it tells is that as you increase the aperture size of the telescope, your angular resolution keeps on improving. Okay, here are some examples of to illustrate the concept of resolution. This is again the image of the sun taken by a small telescope. Now, small telescope, as I said, cannot pick up the details, right? So that's why in this image you don't really see too many details on the surface of the sun, right? This again is a full disk image, but taken with a telescope which is slightly larger, right? So you can already see some of the details showing up in the image. And this one is further image taken by a large telescope of one of these sunspots. So you can see far more details in that image because it's taken with a large aperture telescope. Same example here, image of the Jupiter formed by 5 centimeter telescope, you barely see any detail. Formed by 20 centimeter telescope, some details begin to emerge. Formed by 2.5 meter telescope, which is in space, lots of detail can be seen here, right? So that is the idea about having bigger telescope to make things look more sharper. Okay, but there is a bottleneck that will come to later. Okay, so this here again we show the what is the effect of telescope size and magnification. All three are Jupiter images, but with different magnification and different size of the telescope. This is taken with a small telescope with small magnification. So that's how it looks. And this one, on the contrary, is again a Jupiter image and its Jupiter and its moon's images taken with large telescope and also with large magnification. Right, so magnification makes things look bigger, but not necessarily can resolve or find details. Right, for resolution to happen, you have to have bigger telescope. Remember, magnification is proportional to focal length. Resolution goes as 1 over d diameter. So they relate to different parameters of the telescopes. Okay, all right. So again, when you have small telescopes, it cannot see fainter objects, right? Because aperture is smaller, so it can only collect those many photons compared to a larger telescope. So here is the image of star clusters seen through a small telescope, a medium-sized telescope, and a large telescope. So in a small telescope, you see some stars which are brighter, but not the fainter one. On the other hand, in this, you see not many stars. That's because your telescope aperture was larger, so it is able to see the many more fainter objects. How much time I have? 5 minutes. Oh, okay. All right. This image, this shows the effect of dark skies. As I said, one question was, where do we put these large telescopes? If you want to put research telescopes, install them. What's the right location, suitable location? Now, we can't put it in Bangalore, we can't put it in Mysore because there's too much of light pollution, right? So here is the example. Same telescope, same magnification, just different locations, same part of the sky. This is taken in a light polluted, highly polluted city. This is taken in some countryside, still better, but not good enough. And this is taken under truly dark skies. So you can see the difference between this and this, right? So there's a lot more noise in this image compared to this, okay? So because noise floor is higher, some of the fainter objects are not seen here, which show up here. And same thing applies here, all right? So your telescope has to be installed at places where there are less human settlement, there are less pollution, light pollutions and so on. And usually those places are high up in the mountain. Oh, so I had said that oh, I'm sorry. I'm not able to play this. This was slides I had downloaded. Anyway, okay, so this is an image taken on a hot day. What is not so pleasant about this image? Yeah, there's a heat wave. This was a video. You could have seen that everything looks wavy, right? Now that's happening because of the ground heating. So the ground is heated, hot air rises and mixes with the cold air and creates a lot of turbulence. So the light rays don't travel in straight path. They got all entangled and mix up and give you a very bad image. Same thing happens when the light comes from the stars. It passes through the Earth's atmosphere. Earth's atmosphere is a very dynamic entity. It keeps changing, density changes, temperature changes, pressure changes. So as a result, all these rays, they just don't go straight and land on the telescope. So there is that's called atmospheric turbulence, and atmospheric turbulence basically corrugates the wavefront of light that arrives from the stars. Okay. So no matter how big telescope you make, the resolution of the telescope is not going to improve because of the bottleneck put forth by the atmosphere of the Earth. Okay, so then the question is why to make big telescope if we cannot achieve the desired resolution, right? So the resolution of large telescope is only going to be something like resolution of a 10 centimeter telescope. It will collect more light, but it will not improve the resolution because of the turbulence. But there is a way to correct it, which we call as, well, before that, so the quality of the sight is quantified by something called excellent seeing and extremely bad seeing. These are the things which are measuring the quality of a sight where you're going to place the telescope. So extremely bad seeing means there's a lot of fuzziness in the image, contrast is poor, and image quality is highly unstable. So this is a star image, but it keeps dancing, it's split, and everything happens because of Earth's atmosphere. As you go to the left, the quality of the sight becomes better and better. So this is the place where you are getting a very stable image, almost equivalent to the resolution of the telescope. And this sight, you can say it has excellent seeing, star image is stable, it has a distinct airy pattern, good contrast, and there's no fuzziness. So ideally, we would like to go to places which have very good seeing, right? Okay, so to illustrate this, again you can see, no, I'm sorry, some of these things are not being played, but that's all right. This was the image of the Jupiter seen again at extremely bad seeing conditions and also extremely good seeing conditions. So if I was able to play this, this would be a very nice image, moving slowly, but the features in the image would still be intact. This would be completely washed out image. Okay, so that's the effect of bad atmospheric seeing. Now, there is a technological solution to this adaptive optics problem, and that is that goes something like this. So this is Earth's atmosphere. Before the atmosphere, the wavefronts are all parallel. Once it goes through the atmosphere, there is a corrugation happening, everything is distorted, and so the light comes. This is a telescope, it collects the light. This is your adaptive optics system. Adaptive optics is a technological solution to compensate the degrading effect of Earth's atmosphere. How it does? It's basically a closed loop system. It first senses how much distortion in the wavefront has happened by one of the arm called wavefront sensor. I'm not going to details. Once it senses that, it knows how much corrections to be applied. So there is a real-time computer or control system which measures these distortions, and there's a deformable mirror. This is a specially made mirror whose membrane can be, you can reshape it. There are actuators underneath, so the reflecting surface of this mirror can be reshaped to basically put a shape which is conjugate to the incoming wavefront in order to correct it. So once this whole thing works at a very high speed rate, very high speed, like 1000 corrections per second, right? Because that's the rate at which atmosphere changes. And once this system is in closed loop, you would be able to restore the telescope quality back to normal. So this is the case when your telescope is without adaptive optics. This is the case when the telescope, big telescope, is with adaptive optics, ground telescopes. So you can see lot of difference in the image quality. So so this gives people motivation to build large telescope, because there is a way to get over this problem of turbulence. So I don't know how much time I have, but let me, this may not play again. I should cut short. It's already late, right? Or okay, so all right. So this is next generation large telescope. So I am just showing you three telescopes which are going to be like ELT is the European Large Telescope, 40-meter class telescope, TMT 30-meter telescope, and GMT which has like it's around 18 or 21-meter telescope. No, large telescopes are not single mirror telescope, because you cannot build single mirror of 40-meter diameter, right? The mirror will become too bulky, it will just sag by its own weight. So again, there is a way to get around this problem. Instead of building a big mirror, you make segments, small segments, and put them together. You put them together in such a way that all of them, when put together, would form a single mirror, right? So each of these mirrors has to be aligned very well in order for them to act like a single telescope. Okay, so all these big telescopes are segmented mirror telescopes. ELT has 798 segments, each of size 1.3 meter. TMT has 492 segments, each of size 1.4 meter. And the GMT has 7 mirrors, each of size 8 meter. 8 meter is the largest monolithic mirror that you can cast, not bigger than that. Okay. So this 3 telescope would probably be able to do a lot more new science than what is currently possible with the existing telescopes, which are 10-meter class. Okay, currently biggest optical telescope is roughly around 10-meter class telescope, and those 3 telescopes. This is a James Webb telescope, which is already in the space. It's a 6.5 meter infrared telescope, which is located at a Lagrangian point L2, which is around 1.5 million kilometers from Earth. Okay, it's taken there because it's working in infrared. So all the instruments are very sensitive to the heat and light that is coming from the sun. So you take it as far away from sun as possible in order to avoid the noise that sun causes. Okay, that's the one reason for to be being taken there. So there are many things that these telescopes are doing. I have listed some of those. You can ask me a question later if you have. But there are some challenges in building large telescope, and I have listed some of those. Some challenges are related to how you fabricate these segments, how you put them together. That's also a very big challenge. And of course, since they are a large structure, they should be strong enough to withhold the entire weight of the mirror. So that's another challenge. Structure design is another challenge. To build the adaptive optic system for these, to correct the problem caused by atmosphere, is also quite challenging. And of course, site selection and preparation. So here is the example. Each of these segments will form its own image, right? Because they are separate mirrors essentially. But when you put the segment together, when you do the alignment of these signals, that's called segment phasing and alignment. So ideally, all the images should fall at one point. So you keep adjusting. There are going to be a set of actuators behind each of these mirrors which are aligned. You measure the deflection and align those so that the PSF, there is a single PSF of this segmented mirror telescope, which is equivalent to the mirror size, not the individual mirror size, but the mirror size of the entire telescope, right? So that's another challenge. So I think I would basically, usually this is my last slide that has nothing to do with what I have spoken, but this is a slide which I usually show in most of my talks when I give talk. And so the point is that it's important that you teach your students the core subject, but beyond that also it's essential that you also teach them basically what is scientific methods, what is scientific temperament, what is like logic, reasoning, and skepticism. Teaching them how to question authorities, question whatever that they have in mind, right? So see, we claim that we live in a scientific age. Every day there are new findings, new research discoveries, and so on, right? That's the one side of it. But on other side, it's also age of deception and confusion, right? And that confusion and deception is fueled by largely by social media, which carries lots of misinformation campaign. So we say that we are going to, next plan is human trying to settle on Mars, right? So that's where the technology is right now aiming to reach. Okay, that's one side of it. Another side of it, people still think that Earth is flat. Okay, so that's the bad side of it. Global warming is a reality. Everybody knows it, it's happening. Every subsequent year is warmer than the previous year. But there are people who still deny it, right? And then evolution. Evolution has proved itself so many times from the scientific evidence. But there are people who don't believe in it, Darwinian evolution. They don't believe it because they have not seen a monkey transforming into a human in their lifetime, right? But so that is their limited understanding of how science functions, okay? And there is entirely altogether a different set of people who suffer from this ancient, the past syndrome, basically. They think that past was glorious. All new discoveries were made in past, whether it was high-speed aeroplanes, high-speed internet, or surgery, or whatever it is, right? So all these misconception arises from various reasons, largely because of the misunderstanding of science and also misinterpretation of history or historical facts, right? So people forget, or they don't exercise their ability to separate what is myth, what is history, and what is mythology, okay? So in that case, as a science teacher, as physics teacher, you have special responsibility to train your students to rely on logic, reasoning, and skepticism, because that is the strength of science, so that you can figure out what the real world is, okay? So I think with that I would stop, and the thing is that yes, you should keep questioning. If you can inculcate one students, that in my opinion would be keep questioning, right? Question authority, question people. Just like this morning, the Honorable Vice Chancellor said that economy is doing very well in India. If that is the case, why is that Mysore University is not able to hire new lecturers for years, right? If a country's economy is doing so well, then it should reflect in employment. Still, even in Karnataka itself, majority of the universities are hiring guest faculties. Is that a sign of good economy? That's the question. I'm just giving you an example. Don't accept things just like that. Okay, it's not a criticism of Vice Chancellor. I'm just giving you an example that one should exercise our own thinking in order to evaluate claims that people make. Okay, with that I'll stop. Thank you so much. Questions? Yes. Yeah, please. Yeah, please. No, yeah, please.
Like you said, like you covered all the aspects of the science.
Uh-huh.
You also told about the challenges and how to overcome them.
Yes.
So one thing which I didn't find my answer was, like you spoke about the James Webb telescope.
Yes.
And it's collecting information in the IR region.
Yes.
So I'm just curious, like when you design the telescope, as the lens matter, and also what factor are we going to decide, like this telescope we use for this particular application or for particular objectives see that, like how are we going to select the particular wavelength region?
Right,
What is the criteria to choose particular wavelength?
Okay, so yeah, that's a very good question, because even though largely I spoke about optical telescope or optical astronomy, but the astrophysical processes that are happening on stars, in galaxies, around black holes, in Milky Ways, wherever you can think of, they happen over the entire wavelength range of electromagnetic spectrum, right? So we have lots of information about optics, optical processes that are happening. So something may be dominant in one region of the electromagnetic spectrum as opposed to another, right? So you can get lots of information from visible region, but there is equally a lot of things that happen in infrared region, right? If you want to understand, for example, we can't look deep into the Milky Way. That is because the optical light is absorbed by the interstellar medium. So there is no way to probe the inside of the galaxy by optical astronomy. For that, we need infrared astronomy, right? Infrared astronomy, those are long wavelength electromagnetic waves. They don't get absorbed by the dust and gas which is there in the interstellar medium. So they can look deeper, right? So one of the uses of the JWST is to look deeper, because the light that is coming from farthest corner of the universe, that still reaches us because it's not absorbed, but that's the only infrared reason. So that's why JWST is able to discover galaxies which are just few million years old after the Big Bang. Okay, no other telescope had seen such a thing. Now that had become possible only because of its large size and also the wavelength region in which it is designed. Okay, if you want to study the atmosphere of extrasolar planet, for example, most of the information is in the infrared domain. Okay, so that's why JWST would be very helpful to study areas which are less explored in other domain compared to the infrared domain. Yeah.
Thank you.
You're welcome. Yeah, yes.
You said 8 meter is the largest one.
8 meter, yeah, roughly 8 meter, na, Arun? BLTs are all 8 meter, yeah. So, see, for a mirror to work properly, it has to have like some thickness also, right? Because to support its weight. Now 8 meter so aspect ratio is basically the diameter divided by the thickness of the mirror, right? And so if you let's say make 10 meter class telescope, even if you keep the same aspect ratio, the overall weight of the mirror would be such that it will begin to sag by its own weight. So the shape, for telescope to work properly, its shape should not get affected when it is observing, right? It's on a structure, it is steered constantly to track the objects, right? And if the weight is more, it's going to cause the distortion in the mirror itself by self weight. So that limit is around 10 meters, 8 meter. Yeah.
There is that one more thing can be added.
Yes.
Like since we have to operate over the very dynamic conditions.
Yes.
Like the temperature
changes and everything.
So that may also have the effect on the material property of the mirror.
Oh, that is there, yes. So that is there even in the segmented mirrors. So one has to correct those, but it's much more difficult to correct for the bigger and thicker mirror compared to doing it on a smaller size mirrors segments. Yeah, so the dynamical effects are also important. The slow temperature changes or the gravity load changes when you are observing unit as opposed to something close to horizon and so on.